So at this point, we know how to solve a few different types of equations. We know how to solve linear equations. We know how to solve quadratic equations. This section kind of talks about other different types of equations that we might want to solve and some inequalities. It might seem like a lot is shoved into one section here, but these are types of equations we won't have to solve too often. So I guess they figure let's just throw them all in here real quick for the few times that you'll actually see these. You're more likely to see the things we've already seen before, the linear equations and the quadratics. But okay, first type is a polynomial equation. Those we'll see a little bit in chapter 3, and then you'll see them again if you have to take a few higher level math classes. So a polynomial equation is the result of setting two polynomials equal to each other. And we'll see some examples coming up of that. The equation is in standard form if one side is 0 and the polynomial on the other side is in descending powers of the variable. So that should sound kind of familiar. I think we did that with quadratic equations in the previous section. We saw that there might have been some terms on both sides. You move everything to one side so that 0's on the opposite side and make sure your terms are in descending order of powers. So polynomial equations are a lot like quadratic equations, except their degree might be higher than 2. Quadratic always has degree 2. Let's see. Yeah. So linear equations have degree 1, or in other words, the highest power you see is 1. It might look like mx plus b equals 0. And then you got quadratic equations, quadratic equations. The degree is 2. So it might look like ax squared plus bx plus c equals 0. And then polynomial kind of covers everything. Actually, it includes both of these in linear and quadratic. But if it's neither linear nor quadratic, this is what we'll have to do. We'll talk about what to do when we see those. Now, the degree of a polynomial, we might have already mentioned that in a previous section, right? Is the same as the highest degree of any term of the equation. So again, if it's 1 or 2 the degree, then we already know how to solve them, but we'll kind of see what to do if the degree is a little bit larger than 2. Let's see. And actually in this section, we'll see what to do with the tools we already have. But if there's a polynomial equation and the tools that we have so far are not able to solve it, we're going to see more of these in chapter 3, more complicated ones. More in chapter 3. Yeah, we'll really look at polynomial equations, solving them, and then also graphing polynomials. So there are some polynomials we just cannot solve the way anyway, with the tools we have available now, but we'll see how to do it later. So here's an example solved by factoring. That's one of the tools I was alluding to, that we know how to factor. That's one thing we know how to do, but if factoring doesn't apply, then there's no way for us to solve this. So as they said, first we want to put it in standard form. In other words, just all the terms on one side and then have it from highest power to lowest power. If it's already like that, then there's no need to do anything. But in this example, it looks like I need to move this 8x to the left side. I'll subtract it. And then also this 12. They're both positive, which is why I'm subtracting them. And then here they look like they're in descending order of powers. I've got a third power, second power, first power, and then the 12 has no x, so it's a 0 power. So it's in standard form, check, check. All right, looks good. And then the next step would be to factor. If what's on the left side of this equation did not factor, then there's nothing we can really do at this point. We'll have to wait till chapter 3 to figure out how to solve it. But here I'm looking at just the 4 terms on the left side. I need to factor that. And we saw in the factoring section of chapter P, prerequisite chapter, that the only way to solve how to factor a 4-termed polynomial is by grouping. We had other factoring techniques, but this is the only one that applies to 4 terms. I'm going to kind of split it down the middle and then think about what can I factor out of the first 2 terms. Between 2x to the third and 3x squared, I can factor just a x squared out. And then what would be left? If I take x squared away from 2x to the third, I'd be left with a 2 and 1x. And then x squared multiplied by what would make 3x squared? That would just be a plus 3. And then between the third and the fourth term, I've got negative or minus 8x and negative 12 or minus 12. we said before we need to make sure that whatever we factor out at this point needs to have the same sign as what's above. So that's going to be a minus or subtraction. And between 8x and 12, I can factor 4 out. I think that's about it. If I'm not only factoring a 4, but a negative 4 would be left. Negative 4 multiplied by 2x would give me that minus 8x. And then negative 4 multiplied by 3 would give me that 12. And it would have to be plus 3, because if that 3 was negative, it would be a negative 4 multiplied by a negative 3. That would make positive 12, but I want to see negative 12 to match this guy. So far that's looking good. I've got 2x plus 3 is kind of the like term between this big old term here and this big old term here. And the leftovers are going to go in their own parentheses. I've got x squared from this guy minus 4 from this guy. And now that's equal to 0. Equals 0. There we go. And I know I did factor by grouping once, but once I get to this point, I should see, does anything inside here either factor further? Pretty much you can tell that you're all done with one factor if the highest power is 1, like in this guy. But there's a power other than 1, so I think I might be able to do something else. This would be difference of squares. Difference because there's a subtraction sign, and then squares because x squared is something squared, and then 4 is also something squared. So I'm just going to kind of keep this 2x plus 3 the same. He can't factor any further, but that x squared minus 4 can factor further. I think we said before the difference of squares, it's going to be some binomial with the plus, some binomial with the minus. And then what can you square to give you the first term? What squared makes x squared? Well, of course, that would be x. And then what squared makes 4? You'll put that here. That would be 2. And I think now, kind of like we mentioned before, each factor, the highest power I see on the variable is 1. So that's a pretty good sign that you can't factor them any further. That's as far as they can get. I think I've broken each of them down as far as it goes. Okay, so we factored it. And the next step on the next page tells us now we need to set each factor equal to 0. Let me see if I can remember all the factors. We had 2x plus 3, we had x plus 2, and x minus 2. And it doesn't matter what order those factors are in. If you did this problem and those 3 factors are there, but in a different order, that's fine. It doesn't really matter what order they're in. Now we set each factor equal to 0. There are 3 of them this time. And then solve each little equation. It's like taking a polynomial equation and making it a few different linear equations to solve. That's pretty much what factoring does. And to do that, we use the zero product property like we said before. There we go. I've set each of those 3 factors equal to 0. Now we just got a little bit of arithmetic to do here, or a little bit of algebra, I guess. I'm going to subtract this 3 over to solve that guy. One more step for that one. That's a little more complicated. 2x is now equal to negative 3. The last step there would be to divide by 2. And I think you can feel free to probably skip a few steps. If you can do a lot of that in your head, I'm okay with that. It seems like we solve so many of these. Yeah, if you can do a few steps in your head, don't worry about that. There's one of our solutions. We're going to get 2 more here from the other 2 factors. So this middle factor, x plus 2 equals 0. I just need to subtract 2 from both sides. And that's really the only thing I need to do. There's no coefficient of x that I need to get rid of. X is just equal to negative 2 there. And you can probably tell what's going to happen with the last factor. It's almost the same, but I need to add 2 to both sides to isolate x. Okay, so I'm going to go x is now positive 2 for that one. So there are 3 solutions to this. If they said, what's the solution or solutions to the original polynomial equation, these would be the 3, all 3 of them. In any order, they don't really matter the order. But I think I mentioned before in the homework, usually they'll be like this, x equals blank, and it says, now write your solutions separated by commas, if I remember right. You can say, it doesn't matter what order, they should accept them in any order. Just make sure you write all 3 of them with commas. There's no need to write x equals, because I think for the most part, they already have that for you. I've had students that do that. They'll type in their x equals, blah, 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 and then it'll mark them wrong, which is silly, because they should just program that in there to accept that also, but whatever. Just kind of keep that in mind. If you already see x equals, type there, then I would say no need to type it for yourself. Then the last step is to check the solutions in the original equation. Oh my gosh, I'm not looking forward to that. What were the original? I think it was 2x to the third plus 3x squared minus 8x minus 12. Oh, it wasn't, I forgot. It was equals. These were on that side, huh? I forgot. So that was the guy. If I want to check these, feel free to fast forward this part or skip ahead on this video because it's kind of tedious to do this, but it's important. Yeah. If this was a real life scenario that mattered, why we're doing this, I don't know why, or if this was on a midterm and you have a little extra time at the end and you want to check your answers, this is a good idea. I have to check all three of them. It's going to take a while, but I'm going to start just from left to right. I'll start with the first one we found, just replacing all the x's in the original equation with that. Oops, why did I have? There we go. Ew, this is gross. Oh, I have to use order of operations, so I have to say 2 times. I'm raising -3 to the third power. That's -27. I'm raising 2 to the third power. That's 8. Okay, it looks good. And then I'll figure out how those interact with the 2 in the front. How about I'll square this guy? -3 to the second power is +9. 2 to the second power is 4. And then over on the right side of the equation, there's no power that needs to be figured out. So I can kind of start reducing. This 2 will reduce with this 8 along the diagonal. So it'll leave 4 multiplied by -3. That makes -12. And then I've got a +12 over here. All right, now I need to kind of figure out, how that 2 interacts. Wait, you know what I did? I lost that 3. I'm losing it. This 3, where'd he go? Why is he not sitting there? Oh my gosh. Losing it, losing it. I'm going to put that 2 in the front over 1 and see how that reduces. 2 can go into 8 4 times. So this becomes -27 over 4 because it's just 4 times 1. Okay, how about over here? This 3 can go over 1, and there's nothing to reduce really, huh? It's 3 times 9, I'll multiply that, 27 over 4 times 1 is 4. And now equals, this is -12 and 12 makes 0. And look at this, these add up to 0 also. So that's a good sign. 0 does equal 0, true story. So that means that must have been the right solution or one of the right solutions. X equals -3/2. And then, I think I might just leave it as an exercise. If you want to, you could check the other solutions, x equals 2 and x equals -2 similarly. Might be a little easier though, because there'll be no fractions, but you have to kind of treat it the same way. Take the original equation, replace every x with 2, see if it's true. It should be true. And then move on to the next guy. Take the original equation, set each x equal to -2, and I think it works. If it doesn't work, let me know. Maybe send me a picture of what you did and we can kind of figure out what's wrong, but I think they should both work. All right. So that's really what it comes down to so far is polynomial equations. The only tools we have at our disposal to solve polynomial equations are the factoring techniques. If there's a polynomial that cannot be solved using factoring, then we're going to hold off and figure out how to do it in chapter 3. So there's not a whole lot to say about polynomials anymore. Let's get everything on one side, factor, set each factor equal to 0, bada bing, bada boom. So we're going to move on to a different kind of equation to solve, radical equations. It sounds like it's more exciting than it is. Radical, dude, like a surfer is excited about something, but it's not that exciting, I promise. A radical equation is an equation in which the variable occurs in a square root or a cube root or any higher root, right? See, I told you it wasn't that exciting. We solve radical equations with nth roots by raising both sides of the equation to the nth power. So that's the idea. You're given something like, I don't know, let's say cube root. I'm going to make up a simple one. Cube root of x equals 3. No, maybe not 3. Let's just do 8. No, not 8. Why am I so weird? All right, 7. There you go. If you're given something like that, to solve it, I want to isolate x. And the thing that's keeping x from being isolated is that cube root. So I just say, well, how do I get rid of a cube root? If it was like a coefficient 3 times x instead of a cube root of x, I know how to get rid of that. I do the opposite of multiplying and divide, but here, what's the opposite of cube rooting something? It's actually raising it to the third power. So these two should cancel. So it's similar to multiplying by 3, dividing by 3 cancel each other. A cube root and a third power, a cube, cancel each other out. And it would be the same with the square root. If I had a square root, I would raise both sides to the second power. If I had a fourth root, I would raise both sides, yada, yada, yada. I should have thought this out before. I know 7 times 7 is 49. What's 49 times 7? 343. Ooh, that escalated quickly. So the answer is 343 because the cube root of 343 is 7, apparently. So that's what they mean when they say we solve radical equations with nth roots, because it could be n is, N is whatever type of root, whatever the index is, they call that number the index, the number that's in that little corner of the square root. Nth root, it could be a square root, so n is 2. N is going to be 2 or bigger, whole number, 2, 3, 4, etc., etc. God forbid you have a 10th root someday, by raising both sides of the equation to the nth power. That's pretty much all they're saying. You have a root, just figure out the index. If it's a square root, okay, the index is 2. If it's a cube root, index is 3. Whatever it is, raise both sides to that power and you're good to go. So it seems that the example that I wrote above, it wasn't that complicated, so we didn't really need these steps. But if what's inside the square root isn't just x, if there's more to it or there's a lot of terms running around, these are good steps to figure out how to solve it. Because sometimes it's hard to tell. I kind of know what to do, but in what order should I do it? I might mess it up if I do things in the wrong order. The first thing to do, if necessary, we're going to arrange the terms so that one radical is isolated on one side of the equation. So if on that last example, maybe, I started out with the cube root of x wasn't by himself. What it was, cube root of x minus 2 equals 5. I wouldn't cube both sides right away. I'd isolate the root by adding 2 to the other side and then start raising things to the power. So yeah, again, this is probably for more complicated equations to solve. Okay, once you have the root isolated, then you're going to do what we said and raise both sides of the equation to the nth power to eliminate the isolated nth root. Whatever it is, square root, you raise it to the second power, cube root, raise it to the third power, etc. Third step would be solve the resulting equation. At this point, if you have no more roots left, then you could just go ahead and solve it. But God forbid, if this equation still contains radicals, repeat the steps. So that, if you're wondering, what the heck, how could that be possible? That's what I'd be wondering if I were you. It would happen if, let's say you had square root of x plus 3, and let's say the 3 is not in the root, it's outside, is equal to the square root of, I don't know, 4 minus x or something like that. Then so that's kind of the only time you'd see that, where they say, okay, isolate one of the radicals and then raise it to the nth power. If there's still a root, then blah, 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 blah. Because for this guy, as they said, you want to isolate one of the roots. And I guess one of the roots is already isolated, so I might as well just say we're done with that. And then the next step would be raise both sides to the power that matches the index. These are invisible 2's because it's a square root. So I'd be raising both sides of the equation to the second power. Oh, Lord. And I wish, oh my gosh, life would be so much easier in math if I raise that whole left side of the equation to the second power, it would just cancel the root, but it does not cancel the root, unfortunately, and it's this 3's fault. He's not on board. He should be under the root. Then everything would be nice. Oops. But because he's not under the root, I have to actually think about this as the square root of x plus 3 to the second power. That means the square root of x plus 3 in parentheses multiplied by itself. And then I actually have to FOIL that. Oh my gosh. I have to do this times this, and then this times this, and then this times this. Lord, it's bad. But at least on the right side of the equation, the entirety of the right side of the equation was under the root. So I'm able to cancel the root and the square. So it's just what was underneath the root. But because that 3 kind of ruined it on the left side, he wasn't under the root. I'm having to, yeah, I'm still going to have an equation that results in having some square roots running around. That's the bad news. So maybe we should eventually finish solving that, but I feel like that one I gave you was probably the most complicated one. So I hope you don't mind. I might come back to this. We will come back. I just wanted to give you an idea of when that could happen. If you raise both sides to the power that matches the index, but you're still left with the root, this is the only way it's going to happen. If you have, I guess, at least 3 terms, one of which has no root, but at least 2 of them have a root, I guess, is when you would see this. Oh, why'd I put a 4 minus 4 there? Okay, we'll come back to this. This is like pretty much as complicated as it gets. So I don't really want the first entire example you see to be the most complicated one possible. Maybe we'll warm up. That was just to give you an idea of how the heck that could ever happen. But maybe we'll just try to see an example of that are easy, a little bit easier. And then we want to check all proposed solutions to the original equation after you solve it. So we'll come back to this page, but I want to say for that last step, it says check all proposed solutions to the original equation. Let me see, they're called extraneous. I think I spelled that right. Solutions are possible in these problems. Meaning, it means you did everything right. You did all the steps right. You solved everything right, but one solution doesn't check out. And that happens with these sometimes. It's because you're squaring both sides of the equation. That kind of makes everything messy anyway. Hopefully we'll see one like that. I hope we come across one like that. Let's see if this one gives us that. Let's see. So this one, step one, this is a cute little guy right here. Luckily, there's only one square root or one root in this whole problem. That's how you know you're having a good time. All I need to do is isolate the radical on one side. And the thing that's keeping that radical or root, when they say radical, that just means root. Why are there two names for the same thing? I don't know. Just to confuse us. The only thing keeping that root or radical from being all by himself is this +3. So I'm going to subtract him to the other side, move him over next to x. It's kind of like if there's only one root, the root needs to be all by himself, and everybody that's not in the root, they go to the other side. Now the radical or root is by himself. There was an x on the right side. Now there's a -3. Now I'm going to raise both sides to the nth power. But again, like that example I made up on the previous page, the nth power is 2 again, because this is a square root. So I'm going to take the entire left side and the entire right side and square it. Now keep in mind, I'm not able to just kind of square each individual term. If it looked like this to begin with, I can't just square this term, square that term, square that term. That's not one of the rules of math. The only tool we have is to take an entire side of the equation and square it. So that's why you notice I didn't do x squared and 3 squared. I had to do the entirety of the right side to the second power, even though it would have been a lot easier to do it the other way, but that would break the rules of math. I can't do that. So on the left side, that was the whole point. The square root and the square cancel each other, and I'm just left with what was inside the root, x + 3. On the right side, though, kind of like we wrote on the previous page, I wish I could distribute a second power or any power onto a binomial, but I cannot. I have to write that twice. X - 3 to the second power is not x squared - 3 squared. It's x - 3 times itself, and I have to FOIL that out. And then it becomes a lot more complicated, but at least there's no root left. All right, I'm going to go x times x, and then x times -3, and then I've got -3 times x, and then -3 times -3. On the left, x + 3 equals, okay, x times x squared. X times -3 is -3x or -3x. Another -3x comes from the inner times the inner term, and then I've got -3 times -3 makes +9. Now I'm going to try to move all the terms to one side and combine these like terms at the same time. I'm just going to subtract this x. He can be combined with these 3 x's and subtract this 3 to the other side. He can be combined with that 9. So at this point, I see this is a quadratic equation. The highest powered term I see is an x squared. So it's probably going to be get all the terms on one side and try to factor it. All the terms are on the right side. Mostly because that was less work to do. I didn't have to move a bunch of things. I only had to move 2 things. I've got a 1x squared term. Now I've got a -3 and a -3x make -6x, but one more, -6 minus 1 is -7x. And then I've got +9 and -3 is +6. And now I want to factor that thing. Do I have more room? Yeah, okay, I'm going to move it down here. 0 equals x squared minus 7x plus 6. Now I want to try to factor that. If this doesn't factor, then you're going to have to use the quadratic formula. But I think they're probably going to let it, or make sure that it factors. That would be my first step. And then, yeah, if not, if you can't, then, oops, use the quadratic formula. But for sure, if this was on a midterm or the final, I would make sure this thing factored. Because it's much easier and quicker to factor than to use the quadratic formula. But you could use the quadratic formula if you prefer it. All right, this should factor. It's a trinomial with leading coefficient 1. It should factor, and I just have to ask myself, what multiplied together makes 6 but adds up to -7? I got -6 and -1, or vice versa. Those multiply to make 6 but add up to -7. Now I take each of those little factors and set them equal to 0. X minus, oh, why did I put a plus? X minus 6 equals 0, and x minus 1 equals 0. And each of those will obviously be solved similarly. I just need to add 6 to both sides on this left one. So x is 6 is one solution, maybe. And then x equals 1 is the other solution because I need to subtract 1 from both sides there. So those are my proposed solutions. But these problems are so weird, it's possible that one of those or even both of those don't actually work. And I didn't do anything wrong. It's just that's kind of how these weird problems work. What was it? The original, was it x minus 3 plus 3 equals x? Or was it x plus 3 in the root? I already forgot. Oh, x plus 3 in the root. That's right. It was all positives to begin with. Like that. Okay. So I really need to check. And I think a lot of these you can probably check in your head. So don't really worry about writing it out if you don't want to. So I'm gonna write it out just because I'm worried about making a silly mistake. I'm gonna try to check x equals 6, and then I'll check x equals 1. Check. Okay. So the original equation was square root of x plus 3, and then plus 3 outside the root. And I'm trying to write that without the x, so I can replace it with whatever particular number. Let's see. First, I'll focus on 6, I guess. Here's 6. Replace the x that was here with 6, replace the x that was here with 6, and then simplify this. Oh, I can't take the square root of those until I add them together. 6 plus 3 is 9. I'll think about the square root of that. And then it's plus 3 equals 6. The square root of 9 is 3. 3 plus 3 does equal 6. Okay, checks out. So I'm going to keep this solution. I don't have to throw it away. Let's try to throw a 1 in there. That's my other proposed solution, a 1. Because there was an x on both sides. On the left side, 1 plus 3 is 4. So I'm thinking about the square root of 4 plus 3 equals 1. The square root of 4 is 2. 2 plus 3 is not equal to 1. 2 plus 3 is 5. That's a no. So I have to throw this solution out. And it's not, like I said, it's the factoring, everything I did. It's not like I did something wrong. Just that's how these problems work. And the problem is because you raised, at a certain point in this problem, you raise both sides to the second power. So I think kind of the idea is that the left side could have been a negative number, like a negative x, and the right side could have been a positive. Those are not equal because one's positive and one's negative. But as soon as you raise both sides to the second power, now they're equal. So I think you kind of, at that point where we raise both sides to the second power to get rid of the root, we kind of invited more we invited more solutions that aren't really solutions because, yeah, any number that you could, I guess, it's equal to its, anyway, that kind of thing. That's why, blah, 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 blah. If you don't really care why, don't worry. Just try to remember that you'd always check your solution with these radical equations. Always check, because it's possible, though. I've seen examples where you get two solutions, you check them, and they both check out, and you keep both of them. And I've seen problems where you check your two solutions, and neither of them check out, so there is no solution. You just have to always check. And like I said, don't think that you did something wrong. It's just, that's how these weird problems behave. They're strange. You didn't do anything wrong when you check it and one of them doesn't check out or both of them don't check out. We already did this on the previous page, girl. All right. So now you don't see these very often. Very rarely would you have to solve an equation with rational exponents. Rational exponents mean radicals. Because, yeah, like they mentioned here in this little exponent rule, we know that rational exponents represent radicals. Why is my thing not working? Oh, geez. Wake up, little computer. So, okay, we know that rational exponents represent radicals. If you're raising something to a fraction power, an exponent that looks like a fraction, it really means the denominator of the fraction is the type of root you have. So whatever the denominator was, if it was a 3, it's a cube root. If it's a 2, it's a square root, or whatever. A 4, it's a fourth root. And the numerator is the power that kind of comes after the fact, after you take the root. So in the rare instance where you happen to be having to solve an equation with these types of guys in them, these would be the steps you would follow. A radical equation with rational exponents can be solved by first isolating the expression with the rational exponent. And then we're going to raise both sides of the equation to a power that is the reciprocal of the rational exponent. So maybe just to throw in a super simple one over here, what if I had, e.g., what if I had x to the, wait, I want to look at the next one, make sure I don't use the same power. Okay. How about, wait, what was it again? There we go. How about 4/3 power? I don't know. 4/3 power is equal to 16 or something. If I were, well, actually, you know what I should do? I should say +2 equals 14 or something. Okay, wait. I was trying to think of one that I have to actually do both steps first. If it's x to the 4/3 power plus 2 is equal to 14, my first step would be to isolate the thing that's being raised to the 4/3 power. So I need to move that 2 over first. -2, -2. Oh, wait. Oh, you know what? I'm sorry. This is what happens when I try to make up a problem on the spot. Can I change this to a -2 here? Sorry, that's a minus. So it should look like in the beginning, x to the 4/3 -2 equals 14. And the only way that would change how we solve it is instead of subtracting 2, I want to do the opposite and add it. There we go. Otherwise, this problem wouldn't have looked very nice. I've kind of done the first step. I've isolated the thing that's being raised to the fractional power or the rational power, as they say. And now on the right side, 14 and 2 makes 16. So now they're saying, if I want to get rid of that power, I'm going to raise both sides to the power that is the reciprocal of 4/3. And we've mentioned reciprocal before, but it's been a while. So maybe just to review, reciprocal of a fraction is just take that fraction and flip it upside down. The numerator becomes the denominator and the denominator becomes the numerator. So in this case, the reciprocal of 4/3 is just flip it upside down, 3/4. So that's what I'm going to do is raise both sides to that power, 3/4. And this is 3/4. And the reason that's a good idea is because if you remember, the exponent rule for if you have something to a power and to another power like we have here, this is x to the 4/3 and then to the 3/4 power like that, you multiply the powers. So the existing power that was already there, 4/3, I'm multiplying that by the new power that I gave it. And if you multiply 4/3 by 3/4 or any reciprocal by its reciprocal, any number by its reciprocal, everything's gonna kind of cancel and leave you a 1 power. So this just becomes x to the 1 power, which is nice. That's just x. That's what we wanted. So I guess we were just trying to think, what can I multiply this fractional power by and get 1? That would be the reciprocal. So really on the right side, that's the only thing interesting going on here. I have to calculate what is 16 to the 3/4 power. Remember, the denominator is the type of root you have. So I'm taking the 4th root of 16, and then I'm going to raise it to that numerator power, 3rd power. Okay. So root first, fourth root of 16, that's asking what to the 4th power is 16. And I think that's 2, because 2 times itself 4 times is 16. And then, but I haven't done the 3rd power yet. I have to do that. So x is all by himself on the left side. 2 to the 3rd power is 8. 2 times 2 times 2. So there we go. That would be the solution to that problem. So you wouldn't see these very often. These are very rare that you would see these. But this way, we kind of have a game plan to solve any equation that we possibly can. So they're giving us another one here. This will be good practice. Maybe it's a little harder because it's got more steps. But it's the same kind of thing. First thing I want to do is try to isolate this. The thing being raised to this 3/2 power is just the x. If they wanted the 5 to be raised to the 3/2 power also, they would have to put it in parentheses. If it was this way, then yeah, the x and the 5 they're both being raised to that power, but that's not the case. So I'm going to have to not only move the 25 over, but I'm going to get rid of that 5 as well before I raise anything to any powers. Okay. I haven't gotten rid of this 5 yet, so he's still there. 5x to the 3/2 power. Now 25's gone from the left side of the equation, but it pops up on the right. But again, I have to isolate the thing that's being raised to the power. It's not quite there yet. I need to divide both sides by 5, and then I'll be there. That'll cancel the 5 that was on the left side. Now I'm just left with that x to the 3/2 power equals, now I've got 25 divided by 5 makes 5. Okay, now I'm going to, like we said, raise both sides to the power that is the reciprocal of the existing power. The reciprocal of that power there of 3/2 is 2/3. There we go. So I'm going to take the left side, raise it to the 2/3 power, and the right side and raise it to the 2/3 power. The left side, you can probably just say it's x if you want, but maybe just sometimes I want to see y so I can remember it. Why is that just going to be x again? Because it's the existing power multiplied by the new power I gave it, and everything's going to cancel along the diagonal. So it'd just be x to the 1 power. That makes sense. And now 5 to the 2/3 power, that means cube root of 5, excuse me, and then squared. But there is no cube root of 5, so really that's kind of all we can do. I'm not really sure what's easier. Is this the answer, or leave it as a power? Either one's fine. If this was a midterm problem, you can leave it either because it's not specified how to write your answer. They're both fine, whatever you prefer. But in the homework, excuse me, they might specify. They might say, and leave your answer with an exponent, or leave your answer with a radical. I don't know. They'll specify if they want it a certain way with an exponent. But I don't really care either way. If it's something I'm grading by hand, with, oh, no, a radical. Yeah, either way, yeah, whatever. So, okay, what else? What else? So what other kinds of equations can we solve? The next idea is these are equations that are quadratic in form, they're saying. So it's hard to imagine, but they're more complicated than just a quadratic, but I could kind of rewrite it to make it look quadratic is what these kind of are talking about. An equation that is quadratic in form is one that can be expressed as a quadratic equation using an appropriate substitution. So what does that mean? This would be an example here. Okay, we got, excuse me, x to the 4th plus 5x squared plus 6. So I guess if it is quadratic in form, quadratic always looks like ax squared plus bx plus c equals 0. An equation, quadratic in form. So I would want to write this term as something, and it doesn't have to be an x, it could be something else, squared plus b, whatever b is, to the 1 power plus c. I guess the only problem is that this is a 4th power, but I need it to be a 2nd power. This is a 2nd power, and I need it to be a 1 power. And I've kind of already got the coefficients. A is 1, so that's not really a big deal. And then b is 5, so I don't have to worry about that. And then c is 6. But I need to figure out is there a way to rewrite this to where I can write a x to the 4th power as something squared and x to the 2nd power as something to the 1 power. And I guess the answer is I can write it as x squared squared, and this is x squared to the 1 power. Like that. So then if I guess I squint at this really hard. If I squint at it really hard, which sounds weird, but it looks like something squared plus b times something plus c. And those we know how to solve. So this I can solve kind of using the old-fashioned method or factoring technique or quadratic formula. So at this point, I'm going to write that. I can use either factoring, if this factors, or the quadratic formula. I'd be solving for x squared instead of x. So that sounds crazy, but that means, for example, if you were using the quadratic formula, instead of x equals blah blah blah, you're going to be like x squared equals negative b plus or minus the square root of da 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 da, or ac over 2a, because I didn't really start with the x squared plus bx plus c. I started with the x squared squared plus bx squared. So really that's what we'd have to do. Or if I factored it, it would be kind of a similar thing. If this factors, let's see, I'm thinking of it as it's a trinomial with a squared term, and the leading coefficient is 1. There's a 1 in front. What the heck? So I should be able to do the easy factoring technique. It'll all come down to, are there numbers that multiply to make 6 but add up to 5? Yes. Right? 3 and 2. 3 times 2 is 6. 3 plus 2. Yeah. So it's going to be something plus 2, something plus 3, or vice versa, because those are the numbers that, like we said, add up to 5 and multiply to 6. But instead of just putting an x there, it's going to be this x squared thing here. So it's weird, but yeah, I guess keep that in mind. If your powers that you see in your equation, they're kind of doubled what you would want, they could be quadratic if they were taken down a notch. Like if I cut this power in half and I cut this power in half, That would be pretty easy to solve. I could just factor it. So you could still do that as long as you think of it as the factors aren't going to be just x's, they're going to be x squared. Anyway, it's kind of nuts. Kind of nuts. You don't need to do this very often. This is a rare occurrence where you have to solve these, but I guess they're just like, let's cover all our bases and then we can say we know how to solve everything. And that's pretty powerful. So now I have it factored. I would say, is this a difference of squares? Can I factor this further? But no, because difference of squares has to have a minus here, but it has a plus. Same thing with this guy. If this was a difference of squares, there would be a minus, but it's not a minus. So those, it can't be factored. I'm just going to have to go for it and set each factor equal to 0 and try to solve. Let's see. I'll focus on the left one first. First thing I need to do is subtract 2 from both sides. I think we almost got it. X is not quite isolated because there's a square. X squared is equal to -2. But we know from the previous page of these notes in this section that I need to square root both sides to solve that. But don't forget your plus or minus. We said if you have to take the square root of both sides of an equation to solve, you have to put a plus or minus next to the kind of the numerical part. Plus or minus, this is the square root of -2. But we saw in section 1.4 that I can rewrite that as the square root of 2 and then I. Just looks nicer and it kind of encompasses the negative root and yeah, it makes it simpler. I think the other factor is going to be very similar except a 3 instead of a 2 because we got, almost the same steps except instead of subtracting 2, I'm subtracting 3. So I got x squared is equal to -3. And now I'm going to square root both sides and put a plus or minus. Square root, plus or minus. There we go. Now the left side is just an x. And the right side, I've got plus or minus the square root of -3. Similarly to the 2, I can write it as the square root of 3 and the I. He's holding on to the negative for me. So those would be the solutions. And that's technically, it doesn't look like it, but that's 4 solutions. X is positive square root of 2i, and the I is not in the root. The square root of negative, or the negative square root of 2i. Same thing, but with 3, square root of 3i, negative square root of 3i. So there's really 4 solutions here. If they wanted you to list them all for the homework or something, that's a lot. But as we'll kind of come to see in chapter 3, if you look at the degree of your equation, the original equation, what was his degree? The highest power is 4. That's how many solutions you should have in the end. But they could be repeated. You might have the same solution more than once. We'll see that more in chapter 3. It should have 4 solutions. That's the degree of the degree of the polynomial. Yeah. Interesting. So those you won't see very often, but just kind of, I guess, keep that in mind. I would say don't worry about those too much. They don't come up very often. If you see ones like the previous one we just did in the homework, you can just kind of look back at your notes and follow along. Don't worry about it too much. Yeah. All right. I think one of the very last types of equations we're going to learn how to solve in this section, might never see it again for the rest of your life, but maybe, you never know. Maybe you're stuck on a deserted island and someone there says, here, I'll give you some food or a coconut, or I'll catch a fish for you if you can solve this absolute value equation. And you're going to be like, dang, good thing I took that class and I learned how to solve these absolute value equations. Boom, it's going to blow them away so much, they're going to catch a bunch of fish for you. Anyway, that might be far-fetched. The absolute value of x describes the distance of x from 0 on a number line. So that's a kind of I don't know, an interesting or more thoughtful or visual way to think of absolute value. Because I think when we saw absolute value before, like the absolute value of 4, it just means make everything positive. And if it was -4 is the absolute value is +4. But really all that means is on the number line, let's see, here's 0. The first number we saw in absolute value was 4. How far is that away from 0? It's 4 units away. So that's what really, and the visual way of thinking of absolute value is, that's what it is. It's absolute value of 4 is its distance from 0 on the number line. How far did I have to travel? 1, 2, 3, 4 units. But the same thing with -4. Here he is. 1, 2, 3, 4. How far away is he from 0 on the number line? He's 4 units away. There's no such thing as negative distance, which is why there's no such thing as a negative absolute value. Yeah. That's the visual way to think of absolute value. Okay. How about now? to solve an absolute value equation, we rewrite the absolute value equation without absolute value bars. How do you do that? This is something that's, you rarely see it, but it's something to kind of try to memorize or come back to if you forget. Just come back to your notes and look at it. Rewriting an absolute value equation without absolute value bars. How do you do that? If C is a positive real number and U represents an algebraic expression, then the absolute value of U equals C is equivalent to U equals C or U equals negative C. That sounds kind of crazy. Yeah. But it was kind of like just a very simple one. Let's say instead of U, it was X. I don't know. Absolute value of X equals 2. Something like that. Because what that really means is we don't know what X is, but its absolute value is 2. Or in other words, its distance from 0 on the number line is 2. Who on the number line has distance 2 away from 0? Well, there's only two guys. The guy that's on the right side of 0, that's 2 units away, and the guy that's on the left side of 0, that's 2 units away. 2 and negative 2. So that's kind of the idea. This becomes it becomes two equations where you can remove the absolute value, but the right side almost has a plus or minus. One's positive and one's negative, because this represents distance, and you could be that far away from 0 on the number line on the right side, or you could be that far away from 0 on the number line on the left side. That's why you kind of have to break it into two cases. This is the right side of the number line. This is the left side of the number line. And then, of course, it's going to get more complicated, but we still do the same thing. I guess if there was something on the same side, I would, if necessary, I would isolate the absolute value. We didn't have to on this one, but I just want to mention it in case you see one where it's not isolated. Absolute value, so if it was 2x minus 1, absolute value plus 3 equals 5, then you would have to not only do what the previous page did, but the first thing I'd have to do is move that 3 over to isolate the absolute value. And then I'd go about my business and do what they're describing. We don't have to do that on this example, but I just wanted to throw it out there in case you come across one of those. We're just good to go into the two cases. Okay, so the distance from this number to 0 on the number line is 5. But it could be that we're looking at the right side of the number line, so the number is 5, or it could be that we're on the left side of the number line, so we got negative 5. So every absolute value problem should have two solutions. And that's pretty much it. And I think the hard part of these is just remembering that thing. What do I do with this again? Oh yeah, I remove the absolute values, but I have two cases where the number is positive or negative. That's kind of what you have to do, is plus or minus 5. Yeah, that's a kind of a way to think of it. You can remove the absolute value, but put a plus or minus on the other side, the side of the equation that does not have a absolute value. So it's kind of similar to squares in that way. Remember when you had an x squared, like x squared equals 5, and you square rooted both sides? You had to put a plus or minus, blah, blah, blah. So it's kind of it's got the same feel to that, sort of, except there's no square root. But yeah, now I'm kind of solving two equations, and that solving it is going to be the same on both. This left one, I'm trying to isolate x. I need to move the 1 over and then the 2. Same thing here. It's just that as I move them, I'm going to get different values. So I might just do them at the same time. I need to move that 1 over. So I'm going to add 1 to both sides. Add 1. I'm just kind of trying to attack both of these equations at the same time because they have the same steps. Now 2x is all by himself, and the 1's gone. On the left side, 5 and 1 makes 6. This guy, I've still got a 2x left, and the 1's canceled, but here I have negative 5 and 1 makes negative 4. And the last step for both of these would be divide both sides by 2. And here I'm going to divide both sides by 2, but the answer is going to be different. That's okay. Oops. X equals 3 here. Why was I going to say 4? And x equals negative 2 here. All right, that's it. Beautiful. All right, now last problem. I think this is the last problem, is it? Yeah, okay. My computer's being really weird today. Application. It's hard to imagine any of these types of equations we've solved in real life, but here we go. The formula, this is kind of interesting. H is equal to negative 2.3 square root of I plus 67.6 models weekly television viewing time, H in hours by annual income I in thousands of dollars. Oh, yeah. I was thinking H is the time and it's measured in dollars. What the heck? No. The income is measured in dollars. Okay. I confuse myself a lot of times for some reason. Okay, so this one is hours, time. Okay. I got to remind myself time in hours. So that's why they called it H. I get it, huh? And I is income in what? Thousands? Yeah, thousands. All right. Of dollars. I have to remind myself what's what because I know these types of problems, they give you a number and you got to determine where to put it. I'm either going to put it where I is or I'm going to put it where H is. Depends if they give me time in hours, I'll put it where H is and find I. If they give me income, then I'll put it for I and find H, et cetera, et cetera. What are they giving me here? That's enough talking on my part. What annual income corresponds to 33.1 hours per week watching TV? So they're giving me hours. That's H. Okay. So this is going to represent, I'm going to replace H with 33.1 in this cute little formula here and solve for I. And that should tell me the income. So if it tells me, yeah, this is how many hours of what is it, television someone watches in a week, then this should predict their income. That's interesting, huh? Who studies this stuff? It's so random. Anyway, I'm going to rewrite this equation. We got H equals negative 2.3 square root of I plus 67.6. But I know now that I want to replace H with 33.1. So it looks like the right side is going to stay the same because these numbers aren't changing and I don't know I, so I can't replace it. But I do know H, so that's going to be replaced on the left side there. 33.1. There we go. So I'm going to isolate what I. All right. Solve what I. First thing would be, well, I need to get rid of everything but the root. And the thing that's adding or subtracting is the first thing you should get rid of. Since it's adding the 67.6, I'll do the opposite and subtract it. And feel free to use a calculator on these application problems. We don't need an exact answer here because this is a real life scenario. So I'm gonna, well, I guess I don't need it yet, huh? 33.1 subtract 67.6 is negative 34.5. And then this side we got, all that's left is the negative 2.3 square root of I. I've already gotten rid of this guy. Now I need to divide both sides by the coefficient of the square root of I, the negative 2.3. Divide you by negative 2.3, divide you by negative 2.3. The 2.3 and the negative will cancel from the right side and just be on the left side. Now I have to divide these on my calculator. I've got, let's see, what am I doing again? Oh yeah, divide. All right, 15, no way. Exactly 15? That is crazy. Wait, for real? Yeah, okay. I guess so. That can't be right, can it? 34.5 divided by 2.3. You know, when you get a really nice number like these are decimal numbers. I thought there's no way we're getting a nice number, and we did. Well, they probably designed this problem to become nice. We're almost done. We don't have I by itself, though. I need to get rid of the square root. The opposite of a square root is a square. I need to raise both sides to the second power. So 15 isn't the answer. It's going to be 15 to the second power. Or in other words, 15 times 15. All right. So now we have I by itself. 15 times 15 is 225. So it looks like, what does that say? That, oh man, someone who watches, how many hours? It was 33.1 hours of television. I hope you don't mind I write TV each week. Has, how they describe it? Annual income? No. Yeah, annual income. Does annual have two N's? Yeah, sure. Income. Remember, they didn't say that is the income. It's that many thousands. So it's not just $225. It's 225,000. Nice. Good for this person. That's what I'm talking about. All right, maybe I need to start watching 33.1 hours of TV a week, and then I'll start making more money. What do you think? Is that how it works? No, just kidding. All right, that's it. Thank you. See you in the next section. This has been a fun one for me, hopefully for you too.